Assalamu alaikum dear students. Today we are going to start article number 10.6 in which we are going to learn alternating series and conditional convergence. So here is the layout of the article. It consists of definition of alternating series, then there is alternating series test, alternating series estimation theorem, conditional convergence, rearranging series, and the rearrangement theorem for absolutely convergent series. So first of all, let's define an alternating series. A series in which the terms are alternately positive and negative is an alternating series. There are few examples of alternating series. You can see in every series there is alternate positive and negative terms. And if we observe these series closely, in this case, first term is positive and the nth term is minus 1 to the power n plus 1 some term which depends upon n. And in this case, first term is negative and its nth term is minus 1 to the power n into 4 over 2 to the power n. That is some terms which depends upon n. Again, first term is positive and the nth term looks like minus 1 to the power n plus 1 into some term which depends upon n. So similarly, we can generalize this in this form. So if we have the first term positive, then nth term looks like this, that is minus 1 to the power minus 1 n plus 1, some term which is denoted by un, that is some term which depends upon n. And if the first term is positive, this is the case when first term is negative, and this is the case when first term is positive. So where? Now, what is un here? You can see that if we take absolute value of this, then we have this 1 over n. Then un is actually absolute value of an. So this is a positive number. Now, first series, that is this one, first series is actually an alternating harmonic series. Now, what is harmonic series? You must remember that harmonic series 1 over n, sigma 1 over n looks like 1 plus 1 over 2 plus 1 over 3 plus so on. Now, if we have alternating sign change in this series, that is positive, negative terms, then we have this series. This is called alternating harmonic series and it converges as well. We'll prove in a moment. Series 2 is very well-known geometric series. In this case, first term is minus 2, first term is minus 2 and common ratio is minus 1 upon 2. And since R mod is less than 1, then this series is convergent. And this converges to this sum, which is first term divided by 1 plus R, that is the common ratio of 1 minus R. So negative 1 by 2 makes it positive 1 by 2. So we have minus 4 by 3. So this series converges to minus 4 by 3. And the last series diverges because you can see that its nth term does not approach to 0. So nth term divergent test tells us this series is divergent. Now we prove the convergence of the alternating harmonic series by applying the alternating series test, which we are going to learn in next slides. This test, now one thing which is very important and you should remember it, that this test is for convergence of alternating series and it cannot be used to conclude that such a series is divergent, right? So this is very important to note. So we have alternating series test. This test states that the series, that is the alternating series, u1 minus u2 plus u3 minus u4 so on converges if the following conditions are satisfied. That is, we are going to assume that this is convergent. We have to prove that all these conditions are true. So the UNs are, that is these UNs are all positive, UNs are eventually non-decreasing. Eventually non-decreases, that is, they may behave in some other manner for some finite number of terms, but eventually after some finite number of terms they become non-decreasing. Un is greater or equal to un plus 1 for all n greater or equal to n. This is some finite integer. For some integer n, un approaches to 0. That is, the nth term, this un approaches to 0. Okay, now we look at the case where u1, u2, u3 is non-increasing for n is equal to 1. So we take n is equal to 1 without any loss of generality. If n is an even integer, so we assume that n is an even integer. If n is an even integer, then n is equal to 2m, when m is an integer, right? Any even integer can be written in this form, 2 times some integers. Then the sum of the first n terms, that is Sn, will become S2m. S2m is equal to the sum of first 2m terms. That is, we can write initially it like this: u1 minus u2 plus u3 minus u4 and so on minus u2m. Now since n is even, so n plus 1 is odd, so the sign of this term will be negative. Okay, so since now if according to these conditions, if UNs are eventually non-increasing, then if we arrange this sum pairwise like this, then u1 minus u2, in u1 minus u2, u1 is greater or equal to u2. Then u1 minus u2 is non-negative. Similarly, u3 minus u4 is non-negative, and so on. u2 minus u2n is non-negative because of this condition. Okay. So first equality shows that S2m is the sum of m non-negative terms, right? Now since each term in parentheses is positive or 0, as I told you, therefore S2m plus 2 is greater or equal to S2m. That is, if S2m is this, then what is going to be S2m plus 2? S2m plus 2 will be, we just add two terms in the sum, or we can write it as u 2m plus 1 minus u 2m plus 2. Okay, so this is also non-negative, and by adding some non-negative number into this sum, we will have a greater number. So that is why S2m plus 2 is greater or equal to S2m. So we can conclude this by using this condition number 2. And the sequence S2m is non-decreasing. Okay, so this condition implies sequence S2m is non-decreasing. Now let's analyze the second version of this sum S2m, which is given by this equation. Okay, the second equality shows that S2m, that is this S2m, is less than u1. Now how can we say that? Because again, say by condition 2, if un is greater or equal to un plus 1, then u2 is greater than u3. This is non-negative. u4, this is also non-negative. This is also non-negative. Similarly, u2m is positive because of condition 1. The UNs are positive. Okay, so by using condition 1, u2m is positive. So we are subtracting some non-negative numbers from u1. So S2m is less than u1. Okay, So this is u1 which is positive, and we are subtracting non-negative integers or non-negative numbers from u1. So the whole sum is going to be less than u1, and this sum is in fact s2m. So s2m is less than u1. So we have concluded that s2m is non-decreasing, okay, and s2m sequence is non-decreasing, and s2m is less than u1. Now since s2m is non-decreasing, now from these two results we can conclude that s2m is non-decreasing and bounded from above. s2m is less than u1 means s2m is bounded from above. So it has a limit, and we assume that it has a limit L. Okay, so it has a limit L. This means, and this is the theorem 6 which we are quoting here, by theorem 6, limit of s2m as m approaches to infinity is L. Okay, a sequence an is both bounded and monotonic. And what is monotonic sequence? Which is either non-increasing or non-decreasing. Then sequence converges. If sequence converges, it has some limit L. Okay, so according to this theorem, we can say that limit of s2m as m approaches to infinity is L. Now, if n is an odd number, so this is the case when n is even, right? Now, if n is an odd number, then what will happen? So, let us see. If n is an odd number, then n is equal to 2m plus 1. Okay, where m is an integer. So, keep it in mind, m is an integer. Then, sum of the first n terms looks like this. s2m plus 1 is equal to s2m plus u2m plus 1. Now, since un approaches to 0, so limit of m2m plus 1 is equal to 0 as m approaches to infinity. So, from this we can conclude that s2m plus 1 is equal to s2m plus u2m plus 1, and this approaches to L plus 0 as m approaches to infinity. So, which is equal to L. So, in both the cases, so from equation 1 and from equation 2, combining these two, we can say that the limit Sn as n approaches to infinity is L. Okay, and if the finite sum is convergent, then the series is convergent. So we can say that this series is convergent if it satisfies all three conditions. So we have proved this. So let's apply this test on the series. There is alternating harmonic series, which is series 1 in previous slides. So it clearly satisfies the three requirements in theorem number 15. And what were the requirements? That is, un are positive, un are eventually non-increasing, and un approaches to 0. Okay, so positive, all the uns are positive, that is 1 over n, which is positive, and non-increasing, uns are non-increasing eventually, and un approaches to 0 as n approaches to infinity. So all three conditions are satisfied with n is equal to 1. So it therefore converges by the alternating test. So notice that the test gives no information about what the sum of the series might be. It just helps us state that this series is convergent. We have no idea what would be the sum. So in this case, we can see that from the figure A and figure B. This is the figure A, which shows the harmonic series, which is divergent. We have already proved that. And this is the convergent alternating harmonic series. So this is the divergent. You can see that the sum is increasing indefinitely and there is no limit. of this sum. But in this case, when this series becomes alternating harmonic series, in this case we have this is the first term 1, then we add 1 minus 2 in it, so we have this value, and then we add in this 1 plus 3, we are here. Now again we subtract 1 by 4, we are here. We add 1 by 5, we are here, and similarly we can see that this is converging to some point between 0.5 and 0.75, and actually this is convergent series and converges to natural log of 2. Okay. Now here is a remark. Rather than directly verifying the definition un greater than un plus 1, a second way to show that the sequence un is not increasing is to define a differentiable function fx satisfying fn is equal to un, that is, the value of f match the value of sequence at every positive integer n. And if f prime x is less or equal to 0 for all x greater than or equal to some positive integer n, then we can conclude that x is non-increasing for all x greater or equal to n. So actually this result comes from calculus 1. You have already seen that when derivative is less or equal to 0, function is decreasing, and when derivative is greater than 0, function is increasing. So derivative is less than 0, decreasing, but in case of equal to 0, it can be constant. So this decreasing and constant together, we can say that the function is non-increasing, right? So if you are unable to find the relation between un and un plus 1, you can find this relation by taking derivative and checking the sign of the derivative. If it is less or equal to 0, you can conclude that the series is non-increasing. So we show that the sequence is eventually non-increasing. In this case, we define a corresponding function fx is equal to 10x upon x square plus 16, and now we'll take derivative of this function. Or differentiating this, we have 10 times 16 minus x square upon x square plus 16 whole square, and since this denominator is greater than 0, and this is equal to 0 when x is equal to 4 and greater than 0, less than 0 when x is greater than 4, right? Otherwise it is greater than 0. So less or equal to 0, this derivative is less or equal to 0 for this interval, that is 4 infinity. In this interval, this derivative is less or equal to 0. So we can conclude that un is greater or equal to un plus 1 for all n greater or equal to 0. So it helps us finding the domain or finding the interval for which this is less or equal to 0. So that is, we can say that the sequence un is non-increasing for n greater or equal to 4. Now there is another discussion. A graphical representation of partial sums shown in the figure, in this figure, shows an alternating series converges to its limit L when three conditions are of theorem 15 are satisfied with n is equal to 1. Now starting from the origin of x-axis, we lay off the positive distance S1. S1 is actually U1. So you can see that S1 is equal to U1, right? This is S1. S1 is equal to U1. Here you can see that S1 is equal to U1. Now, to find the point corresponding to S2, S2 is in fact in alternating series is going to be U1 minus U2. Okay, so this is U1. Now, subtracting U2, we are somewhere here. This is S2. So if S1 is somewhere here, we have S2 here. That is, this shows U1, this shows u1 minus u2. Now u2 is less or equal to u1. We don't back up any further than the origin, right? So because of this relation, we don't back up further than the origin. We continue in this seesaw fashion. Again, you can see that where is S3? S3. Now this is S2. We are going to add U3 in order to obtain S3. Again, in order to obtain S4, we have to subtract U4. So we are here. Okay, so continuing in this seesaw fashion, backing up or going forward as the sign in the series demand, but for n greater or equal to n, each forward or backward step is shorter than or at most the same size the preceding step, because un plus 1 is less or equal to un, right? And since the nth term approaches 0, so these are the conditions from the theorem 15. Un plus 1 is less or equal to un, and the condition un approaches to 0 as n increases, the size of the step we take forward and backward gets smaller and smaller. So we oscillate back and forth across the line, across the limit L. So we will oscillate back and forth across this point L, and the amplitude of oscillation approaches 0, right? So the limit L lies between any two successive sums Sn and Sn plus 1. So this you can see that this is S1, this is S2. L lies between S1 and S2. So similarly, S2 and S3. So L lies between S2 and S3. S3 and S4. You can see limit lies between S3. Similarly, S5 will lie somewhere here. So L lies between S4 and S5, and so on. So we can conclude that the limit L lies between two successive sums Sn and Sn plus 1, and hence differs from Sn by an amount less than un plus 1. That is, we can say that L minus Sn is less than un plus 1. So this is what we have concluded from this oscillating behavior. For n greater or equal to n, we can make useful estimates of the sums of convergent alternating series, and actually this discussion leads us to a theorem, and we can say that this discussion is a proof of the theorem we are going to state now. This is theorem number 16, the alternating series estimation theorem. So if alternating series sigma minus 1 to the power n plus 1 un satisfies three conditions of theorem number 15, and these are three conditions for your information: that un are all positive, uns are eventually non-increasing, that is un is greater or equal to un plus 1 for all n greater or equal to n for some integer n, and un approaches to 0, then Sn is equal to u1 minus u2 plus u3 minus u4, so on. This is the partial sum Sn, approximates the sum L of the series with an error whose absolute value is less than un plus 1. That is what we have already discussed. L, you can see from the previous slide, L minus Sn is less than un plus 1. Okay, that is L minus Sn is less than un plus 1. So this is the theorem. The absolute value of the first unused term. Okay, so L minus Sn. How many terms are used in this Sn? Sn is in fact this: u1 minus u2 plus u3 minus u4 up till minus 1 to the power n plus 1 un. So what is the first unused term after this sum? Is un plus 1. So the difference between the limit and this Sn is less than the first unused term, that is un plus 1, the absolute value of the first unused term. So furthermore, the sum L lies between any two successive partial sums Sn and Sn plus 1. We have also observed that this L lies between two successive partial sums. And the remainder L minus Sn has the same sign as the first unused term. So this is the theorem, and the proof of this theorem we have already discussed in previous slide. Okay. So once again, let's read it again so that you can put it together. If the alternating series satisfies three conditions, that is these three conditions of theorem number 15, then for n greater or equal to n, this Sn, that is sum of first n terms of the series, approximates the sum L, that right L, of the series with an error whose absolute value is less than, that is this sum approaches to L. So L minus Sn is not equal to 0. Okay, this error means L minus Sn is some non-zero number. Okay, so this Sn approximates the sum L. Whenever we have approximation, there is an error. So it means Sn is not exactly equal to L. Sn approaches to L, right? So approximates the sum L of the series with an error. And what is the error? From previous discussion, we noticed that this error, absolute value of this error is less than un plus 1. That is, it is less than the first unused term, absolute value of first unused term in this sum. So these u's are the absolute value of the terms of the series, right? So this is the summary of this theorem. And next, what we need to remember, that this L lies between two successive partial sums, Sn and Sn plus 1. Okay, now we try theorem 16 on a series whose sum we know that, and this is the geometric series, right? And we know that its sum, we can find its sum actually. So let's consider S8. You can find it very well, and you know how to find it actually. S9 can be found, and its value is this. So the actual sum of the geometric series, this is geometric series with common ratio minus 1 by 2, first term 1. So actual sum of this series is 2 by 3. Okay, that is L is 2 by 3, right? Now this L must lie between any two sums, Sn and n plus 1, and here is 8. So S8, it must lie between S8 and S9. Okay, so let's see, it satisfies this inequality. You can verify it. So the difference 2 by 3 minus this 0.6, that is L minus Sn. This is Sn. Okay, this is Sn. This is L. So L minus Sn is equal to this, which is positive, and less than 1 over 256. That is first unused term in Sn, which is equal to this. So this is how we can verify L minus Sn is less than un plus 1, and we have verified this with n is equal to 8. Okay, next concept is conditional convergence. Now if we replace all the negative terms in alternating series to the positive terms, we obtain the geometric series. Okay, the series we just have discussed was an alternating geometric series. If we replace all the negative terms in this geometric series to the positive term, then we have this series, this geometric series. And the original series and the new series of absolute values. Now this is the series of absolute values. The original series and new series of absolute values both converge. We have already seen that this is a convergent series, and this is also convergent because this is also geometric series with the common ratio less than mod of common ratio less than 1, which is 1 by 2. Okay, both converge but to different sums, right? For an absolutely convergent series, changing infinitely many of the negative terms in the series to positive value does not change its property of all being a convergent series. So this is absolutely convergent series, and we have changed infinitely many of negative terms in the series to positive values, and it actually does not change its property of still being convergent series, right? So this is the case in geometric series, but this is not true every time. On other convergent series may behave differently, so that is why I told you that this is not the case every time. So this is true in this case, but sometimes the series may behave differently. Now the convergent alternating harmonic series has infinitely many negative terms, but if we change its negative terms to positive values, the resulting series is divergent harmonic series, right? So this is a discussion which leads us to conditional convergence. So let's define conditional convergence. A series that is convergent but not absolutely convergent. Okay, a series that is convergent but not absolutely convergent is called conditionally convergent. And which series is conditionally convergent among both of the series? The alternating harmonic series is conditionally convergent, or it converges conditionally, right? So a series that is convergent but not absolutely convergent, that is if we change all the negative terms to positive terms, the series becomes divergent. So if the series is convergent but not absolutely convergent, this note is very important, is called conditionally convergent. And we have an example of conditionally convergent series, which is alternating harmonic series. So the next example extends the result to alternating P series, and you are very much familiar with the P series, and we have used it in previous sections frequently. If P is positive constant, the sequence 1 over n to the power P is decreasing sequence with limit 0. Therefore, the alternating P series sigma minus 1 to the power n minus 1 upon n to the power P is this series 1 minus 1 over 2P plus 1 over 3P minus 1 over 4P up so on, where P is greater than 0 converges. If P is greater than 1, the series converges absolutely as an ordinary P series. Okay, and if P is less or equal to 1 but greater than 0, the series converges conditionally by the alternating series test. For instance, absolute convergence for P is equal to 3 by 2. So 1 minus 1 over 3 by 2 and so on. For P is equal to 3 by 2, this series becomes this. For conditional convergence, you can consider this series, right? So next, again, few remarks. Now the warning. We need to be very careful when using a conditional convergent series. We have seen with alternating harmonic series that alternating the signs of infinitely many terms of conditionally convergent series can change its convergence status. Even more, simply changing the order of occurrence of infinitely many of its terms can also have significant effect. And we discuss this in next example, in next slides. So rearranging the series. So rearrangement is important, and sometimes after rearranging the series, the nature of the series may change. If this is convergent, it becomes divergent, or vice versa. So we can always rearrange the terms of finite collection of number without changing their sums. We have already discussed, if we rearrange the terms of finite collection, then we do not alter the convergence or divergence without changing their sum. That is, we do not alter the nature, its convergence or divergence. The same result is true for an infinite series that is absolutely convergent. So this is very important. The same result is true for an infinite series that is absolutely convergent. Now there is a rearrangement theorem, and we will sum up all these discussions in this theorem. The rearrangement theorem for absolutely convergent series: if sigma an converges absolutely and b1 b2 bn is any arrangement of the sequence an. Okay, so this series is the sum of the terms from this sequence, and if we rearrange the terms of the sequence by b1 b2 bn, then sigma bn converges absolutely. So what is given if this sigma an converges absolutely? Okay, this series is convergent absolutely, and we are going to rearrange the terms, and new terms are b1 b2 bn. This is a new arrangement for the sequence an. Then sigma bn converges absolutely. So what is given? That is, this series sigma an converges absolutely. And what we are going to do, we have another arrangement. This is also given. We have another arrangement of this sequence an, which is denoted by b1 b2 bn. Then, so with this fact, we conclude that sigma bn converges absolutely, and most important, both the sums, both the series uh, approach to the same sum, that is sigma bn is equal to sigma an. On the other hand, if we rearrange the terms of a conditionally convergent, so this is the case when the series is absolutely convergent. Now, if this we rearrange the terms of the conditionally convergent series, we can get different result. So for conditionally convergent series, this is not the case. We can get different results. In fact, for any real number r, a given conditionally convergent series can be rearranged so its sum equal to r. So here is an example of summing terms of conditionally convergent series with different ordering, with each ordering giving a different value of sum. Right? So let's have a look, and let's have a deep understanding of this concept with the following example. So in this example, we have an alternating harmonic series sigma 1 over n, minus 1 to the power n plus 1 1 over n, and this converges to the number L. Moreover, theorem 16, L lies between the successive partial sums, say S2 and S3. Now consider 2 times L. Now if this series converges to L, so what will be the 2 times L? 2 times L is 2 times this series. Okay, so 2 times this is, and we can write it in this form. We just expanded this sum. First term is 1 minus 1 by 2 plus 1 by 3 and so on. Just repeat this, vary this sum over the over all the terms. So now what we did, this is interesting, we just multiplied 2 to every term inside the brackets. So we have 2 minus 1 plus 2 over 3 minus 2, 1 over 2, that is 2 over 4, 1 over 2. So 2 over 5 minus 1 over 3, that is 2 over 6, is 1 over 3, and so on. So we have this series. Now what we are going to do, now here is a twist. What we are going to do, now we change the order of this last sum. We are going to change the order of this sum by grouping each pair of terms with the same odd denominator. Okay, so here is the odd denominator 3. What is the next odd denominator 3? That is, we are going to pair these two, right? So odd denominator, but leaving the negative terms with the even denominator as they are placed. So 1 over 2 will remain as it is. So next pair will be 2 by 5 and minus 1 by 5. Okay. And what is the next pair with odd denominator 2 by 7, minus 1 by 7, and so on. Now here are the even terms. We'll write them as it is. So in this way, we have this sum. So this is the rearrangement. Okay. Now this 2L becomes this. 2 minus 1 we have written as it is. Next, with even denominator we have minus 1 by 2. Now we paired the terms with odd denominators, that is 2 by 3 minus 1 by 3. Next we have even denominator 4, and we have this term, only one term we have, minus 1 by 4. Now with odd denominator 5 we have two terms, and we paired them up, okay, and so on. So this is the rearrangement of the given series, and we can write it as 2 minus 1 is 1, minus 1 by 2 as it is, 2 by 3 minus 1 by 3 is 1 by 3, minus 1 by 4 as it is, 2 by 5 minus 1 by 4 is 1 by 5. See what happens? So observe it very carefully. This is nothing but the original series. Okay. So what happens? Actually, 2L is equal to L. Wow. So by rearranging the terms of conditionally convergent series 2 times this series, the series becomes the original series, right? So which is the alternating harmonic series itself. So if the two series are the same, it would imply that 2L is equal to L, and which is clearly false since L is not equal to 0, right? So what we have concluded from this discussion, let's see. So we have concluded this example shows that we cannot rearrange the terms of conditionally convergent series and expect the new series to be same as the original one. When we use conditionally convergent series, the terms must be added together in order they are given to obtain a correct result. Okay. So if we change the order, it cannot guarantee guarantee us to lead or to give the same sum. So in contrast, Theorem 17 guarantees that the terms of an absolutely convergent series can be summed in any order without affecting the result. Okay, so summary of a test to determine convergence or divergence we have done so far in chapter number 10 up till 10.6. Number 1, the nth term test for divergence. That is, if an does not approach to 0, the series diverges. Geometric series test, you know it very well. Number 3, P series, and this is also very well known series, and you have already used it in many applications, many questions. Series with non-negative terms, and for this we had integral test. Okay, we had comparison tests, direct comparison, limit comparison, and then ratio and root tests, and then the series with some negative terms. So for this absolutely convergence series test, ratio or root test, or by any other tests of listed above. And also remember that absolute convergence implies convergence. And lastly, alternating series test, sigma and an converges if the series satisfies the condition of alternating series test. So that's all for today.